Thank you, Bob. Really appreciate it. So I'm going to introduce Dr. van der Wal, Berend, my friend Berend. He's a fixture in our history sessions. He always does a great job in bringing up a history paper to our session. But I was jumping from Texas to Norfolk. I was reading his biography, and I was trying to compress it. It's very hard to do that. So I'm going to say the following. He's obviously a Vertical Flight Society technical fellow. He's a very accomplished aeronautical engineer with a lot of patents and a lot of great reputation when it comes to rotor technology and aeroacoustics in Europe. He works for the DLR. He's also a graduate from the University of Maryland and a graduate with a PhD degree from how do you pronounce the
Braunschweig.
I wish I could say it that good.
Perfect.
Yeah. University in 1999. So he's been coming to our session for many times. He has won at least 2 Lindenbaum Awards for the best history paper. What I love about his presentation is that he's very capable, one of those very rare individuals that is able to combine history with technical knowledge on the subject. And that's what I love about his papers. I think you will enjoy this one very, very much. So instead of me continuing this, let me go ahead and give him the microphone and we'll go from there. Thank you very much. Doctor.
Yeah, thank you. Thanks a lot for all these compliments. I guess I have to earn them first. So this year's talk will be about Henrich Focke. You know probably that I'm a fan of Henrich Focke and his philosophy. And recently, the lecture notes of the one and only lecture about helicopter design he has ever given at the Technical University of Stuttgart appeared from an archive. And I was so fascinated by that, so I made a history paper out of it. The content of my talk will shortly be addressing Henrich Focke's 2 years period with the Technical University of Stuttgart and why he was leaving. And a major part, of course, will be about the lecture he is giving there about helicopter design, construction, and manufacturing, ending with a little confusing remarks. On the right, you see Henrich Focke, a little later than the period of his lecture, 5 years later, but it's quite sure that he has been looking about the same at the time. Looks like a grandfather to students, my impression. So in the 50s, in the post-war times, when no aeronautical research and development was allowed in Germany, he had a job first in the Netherlands and then was going over to Brazil, who bought all the developments made already in the Netherlands. And the subject was to develop the quad-tilt rotor Heliconair, but due to spare part issues, he was also asked to develop a 2-seater small helicopter called Beija-Flor, which is a colibri or hummingbird in Brazil. Until in April 54, he got a call from Germany, from the Technical University in Stuttgart, because just 1 year ago, the restrictions have been relieved and the development and manufacturing of aeronautical aircraft will be allowed again in Germany. So every country reestablished their research facilities, universities, increase the number of aeronautical institutes teaching aerodynamics and design, etc. So University of Stuttgart was looking for Henrich Focke to fill the position as a professor and director of the new Institute of Aircraft Design, both for fixed wing and helicopters. As a good complementary research at the Stuttgart airport, Professor Just, who was the chief aerodynamicist of Focke in the war times, was the head of the German Society of Helicopter Research. So research, and he was also lecturing at the university, the theory, and Focke as a practitioner is bringing the industrial background to it. So they thought it's beneficial for both the university and the development in Brazil. He could change his contract to be at the German winter time in Germany and the remainder in Brazil. And he then started in the winter semester 54-55 with a fixed-wing aircraft design. Unfortunately, there's no lecture notes available about that. However, he did not get a contract. He did not get payment. Just one down payment in March 55. There was no institute and no perspective on it, no lab and no airfield. Next year, he returned for a helicopter design lecture I'm talking about today. Same periphery of no institute, no payment, no contract, no call as a professor. He's just on his own. So he was kind of frustrated. Nothing was going forward. And at that time, he was approached by Borgward, a car manufacturer in Bremen, who wants to build not a Volkswagen, rather than a Volks helicopter. Yeah, he was a single man heading the company, and he made all decisions by his own. No one was interfering. So Focke happily agreed and joined a Borgward company and then developed a helicopter. But at the time of certification flights, it went bankrupt, and with it the helicopter development, so he retired. Just as a short background. Now we are turning to the Focke's lecture at the Technical University of Stuttgart with all the content outlined here. I will come on to the content step by step. Of course, I only can give a brief overview of what he's addressing in much more detail in the manuscript, which is a full prosa manuscript of 122 pages, including graphs and sketches. Especially the handwritten sketches I want to bring as well here. To give a student some sort of impression about a helicopter, and hardly anyone had seen a helicopter in Germany at the time. Maybe from Americans, but only the H-51 helicopter or so of that type. So most of the students never have seen one and did not really know what it is about. So he said the principle is, if you have two aircraft that you are tied together by a 1 kilometer long rope, and both will take off at start, they will turn in circles. You might fix the rope in the middle to the ground, and when the aircraft have some sort of excess lift, then they have a centrifugal forces because they are turning around in circles, and the excess lift will bring them up more higher on Earth. And the result of the rope is the coning of the helicopter blades. So this is kind of equivalent to better understand the principle, the balance between lift and centrifugal forces. Then he went over to history of Rotorcraft with the pros and cons of the early designs up to 22. He was thinking that is kind of pioneers with no real success. The period from 22 to 34, there are the pioneers that have at least some sort of little flights, but significantly handling quality and control issues. Until in 35, with the German helicopter developments, there are the first practical helicopters that could stay in the air for a long time. They could reach high speeds, could reach high heights. They are excellent in handling qualities and stability. So these are first practical helicopters considered in his mind. The post-war then brought ahead all the international developments, especially in the United States. And he also addressed the modern tilt rotors at the time, which was a Helicon Air, which is a derivative of his own project in 1943, the FA269, and the current Transcendental Model 1G at 55. Next, he stepped onto the helicopter design, starting with the main rotor, as usually everyone does. But we need to record and keep in mind that in 55 there were no computers. Not at all. They had paper and pencil and charts methods to design something. There was no statistics available about existing helicopters because only very few helicopters were existing at the time. So nowadays it's a complete different procedure to have a pre-design and detailed design. And he mainly built on his own experiences. They always said theory like momentum theory, blade element theory is good and fine, but there are so many simplifications, you better rely on existing measured data, which he had from his former developments. And any theory must be triple-checked with wind tunnel or flight test measurements before being applied, such that you know where it is valid, where it is not. Then he turned to momentum theory, a theoretical result that with even infinite mass could be lifted with rather little power if the radius of the rotor goes to infinite, but of course there's practical limits like the material strength and the mass increase proportional to the third power of radius. And he also addressed compressibility issues if a tip speed is getting too large. He also declares the Horvath figure of merit as a measure of efficiency of the rotor, which in his words, compares the desired, which is the thrust, with the unavoidable, which is the power. But strictly speaking, because it's based on momentum theory, the figure of merit compares the power contained in the slipstream's axial direction only, the swirl not considered, versus the power transmitted to the rotor shaft to generate the desired thrust. For a real rotor, the figure of merit will take a number of roughly little below 0.7, and he was taking that for all his designs, main rotors, tail rotors, whatever, just as a given value, and he did not even attempt to optimize the figure of merit to higher values also. His example helicopter throughout the lecture was the Beija 4 from Brazil, which is a two-seat helicopter shown on the left, with a maximum takeoff weight of 900 kilogram, rotor radius 4.5 meter. Disc loading is also given, and the engine power as a maximum continuous power also. The German development after the lecture, a couple of years later, was the Focke Colibri, and you see there's quite an amount of similarities, but the cockpit is in the front now and the engine in the middle instead of vice versa for the Beija floor. And the overall weight is higher, of course, the maximum continuous power as well. So keeping the red numbers a little bit in mind, I repeat them here. He turns then over to get an impression how many horsepower will be needed in hover at sea level. So he is taking and referring to the Benderman curve, which combines the power loading of a rotor with a disc loading, as we all know from theory. Puts two lines in, one for the ideal rotor, figure of merit 1, and a realistic rotor with a figure of merit below 0.7. And then with the given disc loading of 14 kilogram per meter for the Beija floor, going to the line of a realistic rotor, looking for the associated power loading, which is 6.8 kilogram per horsepower, and the total weight of the helicopter. He ended up with 134 horsepower at the rotor shaft for hovering in sea level. However, that's not all. Of course, we have a number of losses, which are cooling, gearbox losses, hydraulics, avionics, auxiliary devices, and the big part of losses, the tail rotors and their gears. Also, we have to fulfill performance requirements, which are minimum hovering height of 1500 meter out of ground and vertical climb speed of a minimum 1 or 2 meter per second. So he said we need to make an estimate of the maximum power we need in all the flight envelope. And this must be estimated initially, and we take 225 horsepower of the Beija floor because he already had the development in back. Looking to the additional losses, first there's a cooling and drivetrain, and he spent a lot of the chapter and in many details about the design of cooling fans with multi-bladed rotors, which introduce a lot of swirl into the flow, which is sketched on the right. The swirl will change the direction of inflow and the absolute total velocity relative to the rotating fan airfoils. And he, especially in this instance, stated to his students that we would not be good engineers if we do not account for the extensive consequences of all our simplifications in our theory and the neglect of these. So it's a very important sentence that cannot be repeated often and often enough, even today's students. He also said that today's engines usually have a fan for cooling already integrated, and we need not to design by ourselves, which is fortunate. The gearbox losses were addressed in the following. At the time, usually they had combustion engines with a relatively low RPM, but the main rotor, of course, much less, about 1/10 of the rotor engine RPM. Therefore, we need most likely a two-stage gearbox, and every stage requires about 2% of the power. In this case, he judged the engine gearbox losses by 10 horsepower. If we have multiple rotors, side-by-side configurations or front and left rotors, like a tandem helicopter, then we can split the gearbox, one right at the engine and the second one right at the rotor itself, to have a fast-moving gears in between, which do not have this high torque in them because they are rotating fast. Hydraulics and electricity for the avionics and other instrumentation would require about 2 horsepower. And then coming up to the tail rotors, first with the conceptual design of them. address the single tail rotor like the Korsky designs. That is quite nice. They provide the anti-torque, they provide the additional side force for yaw control of the helicopter, but they provide damping only in yaw motion because the tip-pass plane of tail rotor is vertical and doesn't provide anything for the pitching motion of the helicopter in terms of damping. That's why he had invented already and patented in 1938 the twin tail rotor design as sketched here in the graphs, with both tail rotors tilted by 45 degrees to the side, right and left, and they provide both damping in yaw and in pitching motion of the helicopter, which removes the need for horizontal or vertical stabilizer surfaces. They produce not only a side force for torque compensation and yaw control, they also act like a horizontal, like the elevator on a fixed-wing aircraft on the tail, and it was used by him in exactly that manner. Also, at least in the side force, he said, the splitting of the jet of the one rotor by the second one increases the figure of merit of this rotor, so provides more efficiency for this combination than a single rotor. So the tail rotors, however, have to produce a certain amount of thrust, and therefore also as a rotor have a big chunk of losses introduced in the total power estimate of the helicopter. He needs a couple of assumptions first to know what would be the maximum torque of the main rotor. So he made a guess that the maximum power of the main rotor in any of the ultimate flight condition will be in the range of 175 horsepower, including vertical climb speed and hover at maximum height. He guessed the radius of the main rotor to 4.5 meters, similar or the same as a Beta-flow helicopter. And the tail rotors must be separated from main rotor by sufficient amount of distance, in this case 6 meters, to avoid collisions of main and tail rotor blades. The main rotor rotational speed was guessed to 300 RPM, which provides with a radius a torque of 415 meter-kilogram. He stayed in old German units instead of Newton, and Newton meters, he stayed with a kilogram instead of Newton, so the gravity constant is a measure between. For the side force to be achieved by the tail rotor, it will be divided by the 6 meter separation, 69 kilogram in total, plus some margin for yaw control of the helicopter of 9 kilo, totaling to 78 kilogram. So each of the two rotors, half of that, 39 kilogram, but due to the tilt of the rotors by 45 degrees, the rotors have to multiply this number by a square root of 2, summing to 56 kilogram total thrust for each of the two tail rotors. Then you need to estimate the power of the tail rotors required. Again, the Bendemann curve come into use here. He just in the reverse direction, he started with an assumed power loading for the tail rotors of 5 kilogram per horsepower, going to the realistic rotor efficiency curve, provides a disk loading for the tail rotors. Using the disk loading, you can extract the radius of the tail rotor, and then finally the power of the tail rotor in total, including the gearbox. You only need a one-stage gearbox because the tail rotors are running much faster than the main rotor. Only needs one stage of gearbox, so only 2% of losses, summing to 23 horsepower. Then he makes a balance of the powers assumed so far. The total engine power of 225 minus the maximum main rotor power in the ultimate conditions, minus all the losses that have been mentioned before, gearboxes and auxiliaries, etc., and the tail rotor. So we end up with a 6 horsepower margin left over. But in practice, you never end up with a margin you calculate. So he assumes half of it would be in practical use. So there's a lot of practitioner experiences getting into the figure. So in sea level, we end up with an excess power of the main rotor. We assumed in the ultimate condition it would have 175 powers to consume. Plus the excess power of 3 horsepower minus the hovering power at sea level gives the excess power available at sea level, which is 44 horsepower in this case, divided by the mass of the helicopter. You end up with a climb speed at sea level of 3.5 meters per second, which is much larger than the required 1 or 2 meters per second taught at the beginning. He also hinted at the current literature, recent literature in textbooks at the time, 1955. So the first textbook might be guessold at the time of publication. He said there you find often a number of 2 times the excess power divided by mass for computing the hover climb speed in sea level. And he said, he warned the students actually, never use that because I never experienced it. Actually, we have to be fair. This assumption of 2 times excess power is in neglect of all additional losses. We just have to read the textbook carefully and to figure out very quickly that's the case behind. So he concludes with some remarks. Still, many parts in the rotor slipstream, like the airframe, are not yet considered in our calculation, and they also increase, for example, the fuselage drag and affect the slipstream of the main rotor. He also addresses that the slipstream contraction usually is completed much earlier than theoreticians might think from isolated rotors or isolated rotor measurements. And from his observations, it was just 60% of the radius underneath the rotor slipstream is finished. He also addressed the vertical descent, as he called it, vortex ringside or vertical sagging in autorotation, and the entire rotor drag sums up to be equivalent to a flat plate of a circular disk of the rotor radius with a drag coefficient of 1.2. And you find that in practically any textbooks, this kind of physical comparison. How does the helicopter rotor act in vertical descent in autorotation? Addressing climb, also all the airframe parts will be subjected to the climb velocity, but climb velocity is small, dynamic pressure therefore is small, and the total forces of drag of the airframe additional to what is already there in hover is also small, so may be neglected, but we need to be aware of it. He also said in the trim configuration, the helicopter might have some sort of bank or pitch angle, and the main rotor, to compensate that, also will have some sort of flapping, one-per flapping, tilting the disc tip pass plane to side or forward or back or wherever, but not being vertically oriented. That means we have to take the cosine of this as a vertical force to compensate the weight. But the angle is small usually, so you can neglect it because 99% is no big difference. Then he addressed the speed performances of the helicopter. Balancing lift and weight and propulsive force needs to overcome the helicopter drag. And this is a charged method to estimate the helicopter performance curve, say power versus advance ratio. We have shown here 3 charts that he has sketched. The first chart is a lift versus advance ratio for various number of collective control angles, and the chart is valid for only one combination of tip pass plane tilt, he called alpha pi, and a solidity of the rotor. So it's the first assumption, ending up with a collective control for the required thrust at a given speed. The next is a rotor propulsive force, or negative drag if you want, tilting the rotor forward. And enter this with this collective angle, you get a rotor drag or propulsive force coefficient, and it must equivalent to the computed drag of the airframe. If that's not the case, and usually it is not, you have to iterate back and forth, change the angle of attack, or take a different chart, until you have converged results for both advance ratio and collective control for this required condition, and get then to the final chart, or torque versus advance ratio, so you get the main rotor torque and then compute the power as a consequence. What you get is a 1 point of the power curve for one height above ground. Already an iterative process. You have to repeat that for any advance ratio at this height until you have one curve. Then you have to change the height and repeat everything from beginning until there's no solution anymore. And the curve that you get at the outcome is the flight envelope of steady flight in terms of hovering, maximum hovering height, in terms of flight speed and associated height, and ceiling height with associated speed of that ceiling height. That's how it was done at the time, no computers. The outcome of all is an offer to the customer with short description of the vehicle, its weights, properties, performances, computed, and the cost. At the time, estimated to 80,000 D-Marks, Deutsche Marks. And in 55, we had a gross average income of about 4,700 Deutsche Marks, ending up for 7 years of collecting money before being able to buy a helicopter. It's called a Focke helicopter. Not really at the time. Converting this number with inflation rate to today, it would cost 225,000 euro, equivalent to dollars roughly. And the German income currently in average is 55,000 euro. So we end up with 4 years of sparing money. So it's already coming a Focke helicopter today, not then. We went over to construction manufacturing, which for all parts of the airframe and of the helicopter, we need load assumptions. Load assumptions usually are in requirements by authorities, but in Germany, currently no authority was existing. It was just being built up. There were no regulations. So he also mentioned that in Brazil, there are no regulations. And in Brazil, they had to cook their own soup from all regulation internationally available, mainly in the United States, and with own experiences and regulations in the World War times in Germany. To the best of the knowledge. That's how they designed the helicopters. To address the kind of frequency content of loads and the load factors applied to any of the components, and you have to calculate throughout the entire airframe or any strut to a lot of detail that I cannot represent here. You also have to take into account negative load factors because his helicopters had a switching from the helicopter mode to auto rotation. So pilot pressed the switch and then it went to auto rotation. That means a jump in collective. And jumping down in collective by 10 degrees makes a big negative load factor. So he concludes with some comments on responsibility. The designer first, and it must be said over and over, that no regulation from authorities can relieve the designer from its own responsibility of safety. For best, if you are in conventional designs and you have experience, you can compute as before. But for new or unusual designs, you have to triple think and recall and check all the assumptions made before, still valid or not. So your own thinking must be doubled. Regarding authorities, at the time it was already revealing that many countries have exonerated the inspection authorities, leaving the sole responsibility to the designer, even if they cause an accident through an official order which was technically incorrect. So still the designer is responsible. He made everything to order. In Focke's opinion, this must be condemned as immoral. And this is word by word his citation. Then he went to the design phase of the hub and swash blade and articulation of the blades, ranges of controls required for the pilot. He also addressed steady flap leg divergence that you hardly find in literature today, because he had this with the FA 223 development at the first accelerated spin up of the rotor. Slow motion acceleration, no problem. Fast accelerated start up of the rotor, the blades went back first because of their inertia, then lift was developing, blades flapped up, and with a large lag angle, they have a larger increase of angle of attack than the centrifugal force pulls back, and all the blades went up and stayed there. Until very low RPM, they're moving down again. So the sketch already says that, and you can see very easily by your own hands having a flap hinge and a lag after that. So if you flap up and then lag back, you see immediately the angle of attack developing. So it's a cardan hinge by 90 degrees, and that's a natural behavior. And to address this, he suggested 3 measures. One is have heavier blades, larger centrifugal forces eliminates the problem because the blades straighten out again. However, the larger centrifugal force causes more strain and stress to the blades and the structure, which is undesirable. Also become heavier, less useful load on the helicopter. You can increase the hinge offset to the hub, increasing natural frequencies of flap and lead lag, especially lead lag, but lead lag frequency goes up, and the danger of ground resonance increases because approaching 1 per. No good idea. So the kinematic feedback, like a delta 3, as we call it, putting the pitch link outside of the flapping hinge automatically can reduce the pitch angle by flapping. And that's the measure he was introducing to keep it safe and stable, but don't overdo it. You can overstabilize the rotor and make it uncontrollable if doing too much. He entered in all details of the design, and looking to the design of this blade with the main spar and all the ribs, it is a design of the 30s and 40s of the 20th century. His designs of the Focke helicopters, still 30, 20 years after his old designs. Many details regarding the gearboxes and the bearings of the long shafts of drivetrain, and ending up with a complete control set up for the pilot controls, the pedals and the handles. I want to point out one specialty for the left hand, which is the throttle here going fore and aft, combined with a collective right next to it. He complained about Sikorsky helicopters having all elements separate, and the pilot would need 3 hands to operate all of them simultaneously, which is almost impossible. So he had the throttle and the collective on one hand, and if you increase collective, automatically the throttle is opened to provide more power to the engine. So that's his concept, and he ended up with a sketch of his concept of the helicopter, quite similar to the Beja Flow and Colibri, as you have seen before. Ending with a conclusion, Focke's lecture reflects his more than 20 years of experience, first in German war times, then in Brazil, and coming to Germany, continuing with the Colibri helicopter at Borgward. At the time, we always need to recall there were no computers. They had tables of functions, they had mathematical handbooks, they had slide rules to compute something, mechanical computers to just have simple calculations being done on a mechanical way, and paper and pencil. There were no statistics from former helicopters, or extremely scarce, so you could not make a statistic inter or extrapolation from existing models. You had to do by hand or your own experiences. For best, you have measurements from your own former helicopters with charts, and use all these charts and combine theoretical curves with the curves of the measured in the charts. Then you immediately know here is a quite good agreement between theory and measurement, and the other regime, there's a large of deviation. We know there is missing elements in the theory because he relied much more on the experience of the measured data he had performed with his own helicopters, either in flight or in wind tunnel. Use the Brazil helicopter Beja Flow example in all details because Brazil, the helicopter development was not part of a company. It was part of the government organization in a research facility like DLR. And there was also a university on the campus, so lectures and practice were both there. The government made an order to develop something, and this was public domain. There was no secrecy. So he could give all details and even technical drawings to his students and tell, well, it has been made from this kind of steel because of, there's this kind of greasing because of, and so on. So this all is given free. And the students benefited from all these freedom, and here Focke, of course, as well. Using all the charts of theory I already addressed, and the Beja Flow was used as an example helicopter. And the final major thing he wants to give his students for their future career is you are responsible for whatever you do. Thank you very much.